Hello. In this video, we're going to continue with the direct stiffness method. In this occasion, we're going to be talking about post-processing, that is, doing everything after the solution of the system of equations. In this case, stress recovery for our bar elements. First, a little bit of recap. We were solving this truss, this simplified truss, where we have 2 degrees of freedom per node. And we formed in previous videos the system of equations, the stiffness system of equations for the equilibrium of the system. And this system was solved by partitioning the system into the free degrees of freedom and the constrained degrees of freedom. You can solve for the free degrees of freedom by inverting this KFF matrix, which is invertible. And then you can recover the reaction forces by using that simple equation. From that, you can get the displacements at the nodes, and you can plot a deformed shape. This is a trivial matter, it's just a matter of adjusting the nodes so that they fall into their new positions. Usually you have to apply some sort of amplification factor so that they're actually visible, unless you have a really soft structure. What we'd like to know now is what are the forces that are being transmitted by the elements. So for that, we need to go back into the element levels, and we need to see how much each element has deformed, and from that compute the stresses. So for an element, an arbitrary element E that connects nodes Ni and Nj, you can compute, or you can get from the global system solution, its nodal displacements. And from there, you can compute the delta, that is how much the element deformed, that is its final length minus its original length. And from that, you can compute the force that must be carried by the element, that is A over L, that is the area times the Young's modulus over its original length, times this delta displacement. Now this all looks nice in these plots, but we'll see that there's a little bit of development required in order to get it right. So let's compute the original length. The original length is just the subtraction of the nodal positions, that is the length of the bar, and the updated length, that is the final length. You need to add to each of the coordinates, you'll add whatever the displacement was of that coordinate with the one you get from the global system of equations. There should be a minus sign there, that's not a multiplication. So already the original length is that expression, and the new length is that expression, which is a nonlinear expression. So we can think that the delta we're getting is a nonlinear function of the degrees of freedom, or the solution of the system. So from this, let's collect all the degrees of freedom of the element into one element vector, like so. Then we have that the length is going to be a function, a nonlinear function of this vector. And we take this nonlinear function and we do a Taylor expansion about 0. Now the reason for this is that previously the solution of the system of equations was done using a linearized version of the stiffness of the element, right? So it doesn't make sense to compute stresses using a nonlinear version of the displacements. So we do this Taylor expansion, which is just the original length times derivatives with respect to each degree of freedom, and you add those together. And this looks complicated here, but just note that this delta right here, you can notice that you can express the final length as a function of delta. So we can actually compute, if we subtract from this big expression, we subtract L, we get an expression for delta. And it's a linear expression now, because now we can factor out all the degrees of freedoms into the vector and just compute these derivatives. Now we can work with those derivatives to get something that looks nicer, of course. So the delta, as before, are the derivatives of the final length with respect to u times u. So that's the first degree approximation to those. And if we take a look at what those terms look like, we have to compute d of the final length over any one of the degrees of freedom. We'll get this function. So if we develop that a little bit using the rules of differentiation, we'll get this nicer expression. which, as you can see, it involves only the coordinates, original x coordinates of the truss nodes, and the x coordinates or the x components of the degrees of freedom or the nodal displacements. That kind of makes sense, like the stretch. So what this means is basically the stretch only due to the x components. So then if you evaluate this one at u equals to 0, which is what we need to do the Taylor expansion, you get this rather nice expression, the difference of the x coordinates over L with a minus sign. And we can see this is directly the minus the cosine of the element original angle. So if you look at the element in its original position, you'll have node Ni with coordinates xi, yi, and nj with coordinates xj, yj. And if you work everything out, you'll see this original angle, which is the tangent of the, or the arctangent of the displacement in y over the displacement in x. You can see that that works out to be minus cosine of theta a. We get similar expressions for the other terms. So the terms will interchange between minus cosine, minus sine, cosine and sine. We can collect all those into this simplified expression, which is rather nice. So basically, if we want to compute the displacement of the element, given the nodal displacements, u, you just need to take into consideration the original angle the element was forming with the horizontal line and compute this vector, multiply those two things, and you get the displacement. Now with that displacement, you just multiply by the element stiffness and you get the force. So in the end, the final takeaway from this video is that after solving the system of equations, using the global system, you can get the local displacements, nodal displacements of the element. And for each element with its local displacements, you can compute a force by multiplying this delta times its stiffness. And if you do that for all the elements, you can draw something like this. This is the deformed shape of the problem. And with colors I've added the forces resisted by all the elements. So you can see, since there's an applied force here in the original problem, you'll get this minus 86 compression force over here, which is taking all that force, and these are the original parameters that were used in the problem. So after solution, there's a lot of different post-processing steps you can take. You can draw the deformed shape, you can evaluate forces in this case, and we'll see that for more complex elements, we'll need to post-process in order to get different things that are of interest. This post-processing phase is actually very important in the case of nonlinear finite elements, where you actually need to iterate over these forces in order to get the final configuration. And with that, I leave you guys till next video. Thank you.